Hello, fellow problem solvers. So there we're doing a second part of the double counting sort of introduction. And this is the type of thing where I want to show to you that sometimes counting in two different ways can give us problems where we actually can solve problems where we need to find that something exists, sort of construct this. This isn't perhaps the best example because you've seen something similar with when you want to try to find anything that has to do with, say, Fermat's theorem, or you're trying to prove stuff with residues, you'll do some sort of double counting or counting in two different ways. A lot there, but this is another example in number theory. So, it's a problem which I invite you to try out for a minimum of 15 minutes, ideally 45, not more than an hour and 20 minutes. If you want to go along, if you would like to go along with us, just give this a go for the next 5-10 minutes to understand what's happening. Because here's what's happening. We have n is some odd integer, and c1 through cn are some integers, we don't know which ones. For a permutation of the set 1 through n, we define SA to be this sum, a1 times c1 plus a2 times c2, all the way through an times cn. Prove there exist two different permutations, a and b, such that n factorial divides s of a minus s of b. Okay, now this is interesting. And now what is the first sort of thing to do? Well, this problem is really saying, how many permutations do we have? We have of the set 1 through n. Well, we have n factorial different types of permutations. So this is really saying, prove that there exist two permutations which are identical, which are the same. Otherwise, by the pigeonhole principle, like it says, find two which are the same, and if there are no two which are the same, modulo n factorial, that means the permutations are congruent to 0, 1, 2, 3, all the way till n factorial minus 1, right? Otherwise, because we have n factorial different types of residues, we can have n factorial different types of permutations. If no two are the same, it means every single one is represented once. And now this is where we get to use our sort of counting in two different ways. Let's see. So we have that when we go over all the permutations. When we go over, say we sum up all the permutations. A is a permutation, and sum up S of A over all those permutations. On one hand, this is equal to 1 plus 2 plus 3 plus all the way till n factorial is congruent to, actually I should say, congruent to this plus all the way through n factorial modulo n factorial, and this is congruent to n factorial over 2 times n factorial plus 1, right? This is even, this is not, modulo n factorial. We have this on one hand. And now, what is this also equal to? Well, I invite you here to pause for, say, 5-10 minutes and figure out if this is also equal to something else. This is the thing we're counting in two different ways. And here's what it's also equal to. It's also equal to, well, if I'll have a1 be equal to 1 in how many permutations? N minus 1 factorial permutations, right? Because if I fix a1, then all the other ones are going to be, every other single permutation. A2 will be equal to 1 in how many permutations? N minus 1 factorial. A3, A4, An, all will be 1 in n minus 1 factorial permutations. So this is going to equal 1 times every single one of these plus 2 times every single one of these, because 2 is going to be equal to this thing, n minus 1 factorial times this thing, and so on and so forth. So when we're summing all of these permutations up, plus an plus all the way till n times the sum of all of these. Actually, not a1, this is c1, cn, c1 through cn, c1, c through cn. And every single one of these shows up n minus 1 factorial times. So when you get the 1 plus 2 plus 3 plus all the way till n outside of the parentheses, you get this is n minus 1 factorial times n times n plus 1 over 2 times the sum c1, c2 through cn. And now what is this congruent to modulo n factorial? Mind you, we haven't used the fact that n factorial that n is odd yet, so we maybe should be using that now. And this is in fact congruent to, mind you, this thing right here is then n factorial times n plus 1 over 2. This is an integer because n is odd, so n plus 1 over 2. So n plus 1 over 2 is an integer because n plus 1 is then even, times the sum of the ci from 1 through n. And then this is 0 modulo n factorial, right? Because n factorial divides this. On the other hand, does n factorial divide this? Well, if n factorial divided this, this would mean if n factorial divides n factorial over 2 times n factorial plus 1, this would sort of mean that 2 divides n factorial plus 1, which it does not. So n factorial doesn't divide this. We've come to a contradiction then. We've got that this is equal to this, which is this is not a 0, but also this thing is equal to 0 when we count it another way. Both of these ways are legitimate. Ergo, there is a sum. Ergo, not all of these sums are unique, right? Not all of these permutations give a unique sum here, and which means there exists two of them which give the same ones. We take those as A and B, and we're done. The reason this can be unintuitive is because you might think, okay, let me just put C1 through Cn, I only care what they are, modulo and factorial. And then you might think to yourself, could I can order them C1 through Cn, and then maybe I can construct this, right? I can construct what a 1 needs to be, what a 2 needs to be, a 3, a 4, a n, and I can do the same for B, for the sequence of B, and then I can show that these two are actually the same thing. And that seems to me an intuitive route to go by, and that is more local. That is like, let me take one object, and let me construct this object, let me construct this object such that they fit what they need to fit. Versus this is global. It's saying, say no object exists. What happens when I take all the objects together? What do they give me? Right? It's global. And I really want to stress that there's this sort of difference between global, looking at the problem as a whole, and looking at two objects and making them fit. Constructing an object such that it fits what you need it to fit. This finishes up our problem. And as always, thanks for problem solving.